Hi again. So this is another example concerning friction. The problem is an object starts at rest on a planar surface, a flat surface, inclined at angle theta. What is the maximum value of theta for which the object remains at rest? And step one, draw a picture. Read the problem, draw a picture. So I'm going to draw my incline. Here's the angle theta. And here's the object. And the problem is not, uh, it doesn't give you a clue about what it wants you to solve for, right? It wants you to solve what it wants you to solve for a value of theta, but in terms of what? It doesn't tell you what variables theta is going to depend on. So we're going to figure that out by doing the problem. So we're going to write down our sum of forces equations and see what comes out of them, and see if they tell us anything, see what they tell us the relevant variables are. Okay, so the idea is that if theta gets big enough, then the object will slide. And of course, if theta is 90 degrees, then the object, then the plane is vertical. And the object, if it starts here, it's just going to fall, right? There's nothing to keep it from falling. There's no normal force. It's not leaning against the surface. The normal force goes to zero, so it just falls. So you know that for theta that's big enough, for certainly for 90 degrees, the object's going to fall. And you know for theta equal to 0, well, the surface is just flat. The object isn't going to go anywhere. Which tells you that there is some maximum value of theta between 0 and 90 degrees for which the object doesn't go anywhere. So if I start at 0 and I start lifting the plane, eventually the object will slide. But not before I get to some value of theta. And I'm going to write out some equations that I know apply to the situation and see if they give me information about what that value of theta is. And since I've written down the problem, the approach that we have been using is going to work, because otherwise I wouldn't be giving the problem. But if you were coming upon a new situation for which the answer was unknown, you wouldn't know whether the equations worked. You'd write out the equations, see if they worked, if they gave you anything interesting, and if they did, you'd then test it to experiment to see if it made sense, and you'd go from there. You'd keep testing it until you had confidence in it. So step 2 is to draw a free body diagram. So here's my object, and it has a weight which points straight down. It has a normal force on it from the surface because it's in contact with the surface. And yeah, and remember the normal force is a push, and it's normal to the area of contact, so it points up and to the left like that. And there's going to be a frictional force, because in general surfaces in contact have a frictional force. And notice that if there were no frictional force, we've already done that problem, the object slides. So I know from the fact that I'm looking for a value of theta greater than 0, that I'm interested in the effects of friction, because if there's no friction, the answer is theta is equal to 0 and I'm done. But I want something more interesting than that, so I allow there to be friction, which there is in general. And so the friction, I need to decide which way it points. Well, the object is going to start at rest, and I want to solve for it while it remains at rest. I want to solve for this value of theta that's the maximum for which the object remains at rest. So the object's going to be at rest. I know that. And in order for it to be at rest, there has to be a force that counters the portion of the weight that points along the surface, along the incline. And the portion of the weight that points along the incline points down the incline, right? Which you can see from the fact that here's the normal to the incline. And the weight points to the left of that. So the weight is going to pull the object down the incline, which you knew anyway. I mean, you know the object's not going to be pulled up the incline by its weight. So you know the weight points, the component of the weight along the incline points down the incline. And so in order to remain at rest, the friction has to point up the incline. In order for the object to remain at rest, the friction has to point up the incline. And it's going to be static friction because the thing is going to remain at rest because I want to find the value of theta, maximum value of theta, for which it does remain at rest. Yeah, and remember that the static friction opposes the sum of other forces along the surface, parallel to the surface, in order to keep the object at rest. So because the component of the weight along the surface points down the incline, the static friction points up the incline. And what's the other thing I have to do with the free body diagram? Think about that for a second. I have to put in coordinate axes, right? And so convenient axes here, I'm going to choose my x direction to be down the incline because that's the direction that the object would move if it started sliding, and the y direction perpendicular. And those aren't unique choices, right? I could have chosen x to be up the incline. I could have chosen x to be in any direction at all, but it's convenient for x to be along the incline because I'm interested in what's happening in that direction. Okay, so that's free body diagram. Step 3, write equations. Now, I don't know at this point, well, I know, but it may not be obvious at this point what kind of answer is going to come out of this. So I'm just going to write down equations and see what the equations tell me. So first equation, sum of forces in the x direction. Well, I've got the component of the weight that's in the x direction. And if you remember my technique for finding the angle in this picture, if this angle theta goes to 0, so that the incline is no longer inclined, it's horizontal, then the x direction goes horizontal, the y direction goes vertical. The normal force goes vertical. So the angle between the normal force and the weight goes to 0 because the weight doesn't change its direction. It doesn't depend on the angle of the incline. The normal force does, and the static friction does, but the weight doesn't. So when theta goes to 0, this angle will go to 0 because the normal force will become vertical, the weight will remain vertical downward, and so that they'll be anti-parallel. So this angle will be 0. And so this angle is the same as this angle because this goes to 0 when this goes to 0. Remember, it's just my trick for figuring out how to label this. Okay. Sum of the x components of the forces. I've got the weight points in the positive x direction, right? Because it points to the left of the vertical. And to the left of the vertical is the positive x direction. So it's going to be plus mg times cosine or sine. Well, the angle theta is adjacent to the vertical. So the vertical gets the cosine, the y direction gets the cosine. Therefore, the x direction gets the sign. And it makes sense because when theta goes to 0, sine theta goes to 0, meaning that there's no component of weight along the incline, which is the case when the incline is not inclined, right? When the angle here is 0, then the weight has no component along the incline. The incline's flat. It's not inclined when the angle is 0. So the weight, which is down, has no component parallel to the incline. So the sign makes sense because it goes to 0 when theta goes to 0, which is what you know has to happen physically. So I'm just checking that I got the right trig function there. Okay, then the static friction points in the minus x direction. So the x component of the static friction is minus, because it points in the negative direction, the negative x direction, the magnitude. And it's just the entire magnitude. You don't have to worry about cosine or sine because all of it is in the minus x direction. Normal force has no x component. It's in the y direction. So this sum of forces is equal to ma sub x. And we want the acceleration to be 0 because the object is going to remain at rest. So its velocity is not going to change. So we want the acceleration to be 0 to match our situation. So that's the first equation. Second equation is sum of forces in the y direction. And we've done this before. I think, maybe not. That the normal force is in the plus y direction, and it's all in the y direction, so it's going to be plus Fn. Static friction has no component in the y direction, so its y component is 0. And mg points in the minus y direction, right? It's pointing down, which is below the x-axis. So it's minus the magnitude mg, and then cosine or sine, well, the angle theta is adjacent to the y direction, so cosine. And that equals ma sub y, and there's no acceleration in the y direction because the object is not going to leap off the incline. It's not going to start flying. So this is 0. Yeah, there's no motion in the y direction, so the velocity doesn't change in the y direction, so the acceleration in the y direction is 0. Okay, and as you go through these problems, do double check. So for the free body diagram, did I leave off any forces? I've got weight, normal force, static friction. Nothing else is touching the object. There's no hand pushing it. There's no rope attached to it. So those are all the forces. Good. And then I have my two equations, which is what I was looking for here. Okay, now, step 4, I'm going to solve for something. But what am I going to solve for? Okay. If I look at equation 1, I want to find the maximum value of theta for which the object remains at rest, right? For which this acceleration is going to be 0. Well, the maximum value of theta corresponds to the maximum value of sine theta, because sine theta increases with angle from 0 to 90 degrees. It's a good thing to remember, just so that the things will make sense with these problems, that sine theta and cosine theta obey or have these values for particular angles. So for 0 degrees, sine theta is 0, cosine theta is 1. For 45 degrees, actually, let me do 30 degrees, sine theta is 1/2, cosine theta is 0.866. Ah, let me make a bigger table here. This is useful. So sine theta, cosine theta, okay, and I'm going to do 0 degrees. I was just going to do 3 values to begin with, but let me do more. 30 degrees, 45 degrees, 60 degrees, and 90 degrees. So it will be helpful if you remember, especially that sine of 0 is 0, cosine of 0 is 1, sine of 90 is 1, cosine of 90 is 0. Sine of 45 degrees is 1 over root 2. Cosine of 45 degrees is 1 over root 2. 30 degrees, the sine is a half. The cosine is root 3 over 2. And 60 degrees, the sine is root 3 over 2. And the cosine is a half. The most important ones to remember are sine of 0 is 0, cosine of 0 is 1, sine of 90 degrees is 1, cosine of 90 degrees is 0. So I'm using that fact here that sine theta increases with angle from 0 to 1 as the angle goes from 0 to 90 degrees. And so coming back to what I was saying, as theta increases, because I want the maximum theta, sine theta is going to increase. M and G don't change. So the static friction is going to increase. Because if I solve equation 1 for static friction, I'm going to get, if I add Fs, so I start with mg sine theta minus Fs is equal to 0. If I add Fs to both sides, I come up with static friction is equal to mg sine theta. And if I put in that theta is its maximum value, then m and g don't change. Sine theta increases to its maximum value, so static friction increases to its maximum value. So I get that Fs max is mg sine theta max. Okay, that's sort of interesting. Let me see where I can go from there. So Fs max is coefficient of static friction times the normal force. And I haven't done anything to the other side. So that's getting me somewhere, right? Now, the normal force, I can possibly solve for the normal force in terms of the weight, right? It's a common thing. The normal force depends on the weight. Let me take a look at equation 2. So equation 2 says that normal force minus mg cosine theta is equal to 0, because the thing's not leaping off the track. So I want to solve for the normal force here to plug in there. So I add mg cosine theta to both sides. And I get normal force is mg cosine theta. Okay. So let me plug that into this equation. So I get mu sub s times mg cosine theta, which is plugging this in for the normal force, is equal to, and by the way, notice that I'm talking about the maximum theta here. So let me make a note of that, because I want to solve for the maximum angle. Yes, that's what I'm solving for. The maximum angle for which there's no motion, for which the thing doesn't slide down the incline. And so that is, I'm plugging in here, so mu sub s mg cosine theta is equal to mg sine theta, where theta is theta max. Okay, so something nice happens, right? The mass cancels on both sides, right? If I divide by mg on both sides, multiply by 1 over mg, I get that the static friction coefficient is equal to, oh, I'm sorry, times cosine theta max, because the mg is going to cancel, equals mg cancels sine theta max. Okay, so that's nice. I have an equation that relates the maximum angle to the static friction coefficient, and there's nothing else, which is sort of sweet, right? It doesn't depend on the mass of the object, doesn't depend on the area of contact of the surfaces. And notice that we never talk about the area of contact, because friction, to a very good approximation, does not depend on how big the area of contact is. It depends only on the normal force and the coefficient. So yeah, so this is nice. It relates the angle theta max, what we were trying to find, the maximum angle for which there's no sliding, to just a single measurement, a single value that characterizes the situation, which is the static friction coefficient between the object and the surface of the incline. And then I'm just going to, so that's what I was looking for. Now I'm just going to clean it up a little bit. I want to get theta max by itself, so I'm going to move everything with theta max to one side. So I'll divide by cosine theta max on both sides, and this is just cleaning up the expression. It's just to make things look nice. So I get mu sub s is equal to sine theta max over cosine theta max. And if you remember from SOHCAHTOA, sine is opposite over hypotenuse divided by cosine, which is adjacent over hypotenuse. And when you divide, you multiply by the reciprocal, so it's opposite over hypotenuse times hypotenuse over adjacent. Hypotenuse cancels, that's opposite over adjacent. Ask yourself, what is opposite over adjacent from SOHCAHTOA? It's tangent. So we've got mu sub s is equal to tangent theta max. And if I want to solve for theta max, which was the problem, this is a very nice equation. I mean, if I were publishing this, I'd probably leave it like that. Yeah, we were asked for theta max, so take an arctan. Just to me, mu sub s equals tan theta max looks really nice. But if you take an arctan on both sides, the arctan of the tangent, that goes away, and so you get that theta max is equal to arctan of mu sub s. And that's really nice. It's an equation for how far you can tilt an incline before an object sitting on it with coefficient of friction, static friction mu sub s between the object and the incline starts slipping. And you can try this experiment at home, right? If you have some sort of flat surface, take a book and put a penny on it, right? As you tip the book upwards, eventually the penny will start sliding. If you measure the angle using a protractor between the surface of the book and the horizontal, so if you're doing this on a table, you can put a protractor so that you measure the angle between the bottom of the book and the table. Then that will be a measurement of the static friction coefficient, right? Because this also means that the static friction coefficient is equal to tan theta max, which is one reason I like this equation. you can use this equation to measure the coefficient of static friction by measuring the angle theta max at which the object on the inclined plane starts sliding. So yeah, I mean, if you have a protractor, you can try that. You don't even need a protractor, right? Um, you can measure tan theta max, right? If this is the incline, and say you've inclined it so that this is theta max, you can take a ruler and you can measure the height and you can measure the length, and then tangent of theta max is just opposite the height divided by adjacent the length. So your coefficient of static friction is h over L. How about that? So anyway, yeah, so all you need, no fancy equipment, not even a protractor. You can measure the coefficient of static friction between an object and a surface, or really between two surfaces, with this tipping method. You incline the surface until the object on it starts sliding, and then the coefficient of static friction you've measured to be this length divided by that length. So I hope that's been useful. As you can tell, I find that sort of fun. And thanks for your time, and I hope you have a good day. Until the next time, I get to wish you a good day.